All right, welcome to the DDPS seminar, everyone. Let's go over logistics. First, please mute yourself during the talk unless you have questions. If you have questions, you're welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Ionut-Gabriel Farcas, who is a postdoctoral fellow at the Oden Institute for Computational Engineering and Sciences, the University of Texas at Austin, where he is currently mentored by Dr. Karen Wilcox and Dr. Frank Janko. Prior to joining the Oden Institute, he did PhD in the chair of scientific computing in the computer science at the Technical University of Munich at Germany, under the supervision of Professor Hans Bongartz, graduating in 2020. His research interests are diverse and are mainly concerned with the computational methods for large-scale real-world simulations, non-intrusive model reduction, fold and inverse uncertainty quantification, sparse grid approximations, multi-fidelity methods, and high-performance computing. And as application scenarios, he's mainly focused on combustion in rocket engines and turbulence in fusion devices. That was quite a lot. And his list of awards include being a two-time winner of a Best Poster Award at the SIAM Conference on Computational Science and Engineering, being the Romanian Student of the Year at the postgraduate level in Europe in 2019, and being the recipient of the Heinz Schwarzel Prize for his PhD thesis, which is awarded to the best PhD thesis in fundamentals of computer science that was submitted to any university in Munich previous 2 years. Okay, today Ionut will present an interesting topic, which is learning hierarchies of reduced dimension and context-aware low-fidelity models for multi-fidelity Monte Carlo sampling. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton by asking one random question as usual. Today's random question is, do you have any superpower that others do not have?
That's a very good question. I can say that maybe not. Maybe my sort of power is that I don't easily give up. So that's something that I think is useful for a researcher, but otherwise, not really, no.
All right, good. It's all yours.
Okay, thank you so much. And thank you so much for inviting me to give a presentation today. It's a big honor to speak in this seminar. And it was already mentioned, today I will talk about some of my research in the realm of uncertainty quantification. And mainly I will focus on the use of low fidelity or reduced models, something that is typically discussed in the context of this seminar, but in the context of multi-fidelity methods for uncertainty quantification. And this work started towards the latter stages of my PhD in Munich. And I want to acknowledge my collaborators, and mainly Ben Persdorfer from the Courant Institute in New York, and also one of my students from Munich, Julia, and some of my current and past mentors, Frank Janko, who is a physicist from the Max Institute, and Tobias Neckel and my PhD supervisor, Hans Bongartz. All right, so I have divided my presentation into 4 parts. So first, I will start with a brief motivation of this work, and then I will discuss about the first algorithm, the first idea that is mentioned in the title, meaning multi-fidelity sampling methods with reduced dimension of fidelity models. Then I will present the third section, which is the second idea, the second part of the title, which is multi-fidelity methods with context-aware low-fidelity models. And then I will draw some conclusions at the end. And as application scenarios for these algorithms, I chose some interesting plasma physics test cases But I want to stress from the beginning that even though I apply them in some specific problems in plasma physics, these algorithms are generally applicable to a wide range of problems. So if you are interested to test these algorithms into your applications, then I would be more than happy to discuss further with you this. So let us begin. So the motivation for this work and the motivation in general for my research is to deal with higher dimensional real-world problems. And in this case, we deal with the problem of uncertain propagation. So what do I mean by that? Well, by briefly speaking, by uncertainty propagation, I mean the problem in which we are given a high fidelity model, typically stemming, for example, from the serialization of a PDE. This model is deterministic, but it depends on uncertain inputs. And these inputs can be, for example, initial boundary conditions or scalars that characterize the system. So if you think, for example, of a CFD simulation, then the Reynolds number could be the uncertain parameter. And these uncertain parameters parameterize the high fidelity model, and the task of uncertainty propagation is to propagate the uncertainty in the inputs through the model and compute quantities of interest. So for example, in a CFD simulation, the pressure at a certain location in space or the velocity. And then the final task is to estimate, for example, statistics of this quantity of interest. And in this presentation, I will think about uncertainty propagation as an outer loop application, meaning that I treat the given model as a black box in the sense that I do not modify it, but rather I only query it by giving inputs, and I expect to get a well-posed output at the end. And because we deal with parameters that are uncertain and therefore live in a, let's say, probabilistic domain, then what happens is that instead of doing one simulation as we do in deterministic problems, we have to do an ensemble of simulations. And once we do this ensemble of simulations, then we collect an ensemble of outputs, which we post-process to compute quantities of interest. And of course, when we deal with large-scale applications, then the larger the ensemble is, the more challenging the uncertainty propagation task will be, because this will be computationally very expensive. And as I mentioned, the application of interest for this work is plasma physics. And here you have to keep in mind that if we do a realistic nonlinear simulation, this can take days and even weeks just for one run. So doing uncertainty propagation in such applications can be very, very challenging. And how do we deal with these challenges? Well, of course, we have the field of model reduction, which is specifically designed for this type of, to address this challenge. And instead of using the high fidelity model in our simulations, which can be computationally very expensive, we aim to use a reduced model. We invest a bit of effort into finding a reduced model, and then we use the reduced model for the task of uncertainty propagation. So we know about reduced models that generally they are less accurate than the high fidelity model, and that generally we have a trade-off between their accuracy and cost. And in the context of multi-fidelity methods, we think about reduced models or low fidelity models that I will use in this presentation, or surrogate models broadly. So we can think of, for example, data feed models. And now we have the field of machine learning that provides such models, or classical interpolation or regression. We can have coarse width approximations, or we can have projection-based reduced models, such as reduced basis or proper orthogonal decomposition, or we can even have simplified models or linearized models. And if you think, for example, in turbulence, we typically have available several models for such a process. So we can think of all these generically as low fidelity models. So how do we do this in classical uncertainty propagation? Well, if we have a low fidelity or reduced model, then the classical approach is to replace the high fidelity model with a low fidelity model, where the keyword here is replace, which means that if I replace my high fidelity model with a low fidelity model, then the accuracy of the low fidelity model will drive the accuracy of the uncertainty propagation task. Now, as we know, when we have a linear problem, this is rather, we know how to do it. We know how to find accurate low fidelity models. But when we go to nonlinear problems, for example, then of course the test becomes more challenging. And really what's important to have here is a low fidelity model that is somehow certified. So we know the error that we make. Because again, the error of this model then determines the error of the accuracy of the uncertainty propagation procedure. However, as the title suggests, in this work, we do not focus on the classical model reduction approach, but rather we take the multi-fidelity perspective, in which instead of replacing the high fidelity model with a low fidelity model, we combine high and low fidelity models, having a model hierarchy. So basically we do the same task, but not using just one model, but actually using multiple models at the same time. And what is interesting about this, and then I will show you at length in the rest of the presentation, is that in multi-fidelity methods, even wrong models can be useful. And of course, by wrong, I don't mean complete nonsense, but rather models that on their own would not necessarily be very accurate. And in the multi-fidelity sampling algorithm that I will talk about, basically, it guarantees the high fidelity accuracy because it keeps the high fidelity model in the loop. However, the general idea is that we put the least effort into the high fidelity model, and then we put the most effort into the low fidelity models, which are cheap to evaluate. And for an overview of multi-fidelity methods, I recommend looking at the survey that appeared in SAM Review a few years ago. Okay, now setting the background, I will talk about the first idea in this presentation, which is enhancing multi-fidelity Monte Carlo sampling with what I call reduced dimension low fidelity models. So basically the research questions that we try to answer here are the following. The first one is rather generic and is very specific to multi-fidelity methods in general. And it is, if we are given a hierarchy of low fidelity models, how can we use them to speed up computations, for example, in uncertainty propagation? And more specific to this algorithm is that how can we use information about low fidelity models to further speed up computations? And if we draw a picture of this, then we have an outer loop in which we have the hierarchy of high and low fidelity models. And then our questions here is, how do we use this hierarchy to speed up computations? So to set up some notation, so we are given a high fidelity model, F, that depends on D random inputs, and it has an evaluation cost W0. And for large-scale computations, then we know that this W0 is typically very large. And let's say we are given a budget P in seconds, which is the budget that we have for performing uncertainty propagation. And then the task at hand is to estimate the linear functional, which is the expectation of the output of the system. Now, if we were to use a standard Monte Carlo estimator, that we know that we will draw random samples from the distribution of the inputs. We'd evaluate the given model at each sample, and then we'll take an average of these evaluations. And we know that this estimator is an unbiased estimator with a mean squared error that is essentially its variance. And this depends on the variance of the model, the budget, and the evaluation cost. Now, the good thing about this mean squared error estimator is that it doesn't depend on the number of random inputs, so it's independent of the dimension. However, this decays very slowly. And if you think of F as being the high fidelity model, and let's say one evaluation takes a few hours or a day or a week, then we can afford only a handful of such simulations. And if we deal with a high dimensional parameter space, then this task becomes prohibitive. And then the question arises that how can we improve the mean squared error of the standard Monte Carlo estimator? And basically we have two options. So one is to increase P, which of course we don't want to do because this means that we need to do more high fidelity evaluations. And the second one, which we take in the remainder of this presentation, is to decrease the variance of the estimator. And this leads to so-called variance reduction techniques. And the multi-fidelity algorithm that I will present in here is essentially a variance reduction technique. So in contrast to the standard Monte Carlo estimator, in multi-fidelity estimators, basically we combine the high fidelity model and the low fidelity models. We compute Monte Carlo estimators for each of these, And then we find a multi-fidelity Monte Carlo estimator, which is a linear combination of these estimators. So this is where all models come into play. And basically, we start with an estimator of the high-fidelity model, and then we add weighted corrections of estimators depending on the low-fidelity models. And basically, in this algorithm, the accuracy of the low-fidelity models is ascertained using the correlation coefficient between these models and the high-fidelity model. And also what's important, in addition to the metric for accuracy, is their evaluation cost. So not only we care about accuracy, but also we care about evaluation cost. So let's say for simplicity that we normalize this evaluation costs, so they are relative to the high-fidelity model. And if we are to fast forward and compute the mean squared error of this estimator, we get again that this is an unbiased estimator. So its mean squared error is equal to its variance. And we get an expression that basically is a product between the mean squared error of what we get when we use only the high fidelity model and an expression that depends on the correlation coefficients and the normalized costs of the models. And basically this expression here is the one that gives us the variance reduction. So basically if this expression is smaller than 1, then we get variance reduction. And the smaller this expression is, then the more variance reduction we get. So we see that in the multi-fidelity algorithm, we have two important ingredients, which is the correlation coefficient of the low fidelity models with respect to the high fidelity model and their evaluation cost. So now, in the standard formulation of this algorithm, it is assumed that all low fidelity models are given, so we have them available, and also they have the same number of parameters as the high fidelity model, which of course is not an unreasonable assumption because in general, when we construct parameterized reduced models, which only have the same number of parameters as the high fidelity model. But the question that we try to answer here is, can we still improve on this and speed up computations by using information about the parameters? And of course, the answer is yes. And as I will show you in a numerical example, we consider here so-called reduced dimension low fidelity models. So let's start with the application itself. So I will not spend too much time explaining this application because this would require a separate presentation. But nevertheless, to give you an idea, so here we focused on an application in plasma physics, which is of great interest for the community at the moment, in which we dealt with suppressing turbulence in fusion reactors with energetic particles. And to this end, we use this simulation code gene, which is developed in the group of Frank Jenko in Garching. And we consider the realistic parameter set based on a publication that considered the fast particle stabilization in a jet discharge, which is a reactor in the UK. We consider 5 particle species here, deuterium ions, electrons, and also 2 fast particles. And to be realistic, we also consider carbon impurities. And our high fidelity model here has about 250,000 degrees of freedom. And we consider simulations for budgets from 50,000 to 1 million. And as low fidelity models in this problem, we considered sparse grid approximations. And basically we considered an interpolation sparse grid low fidelity model that is constructed adaptively using sensitivity information about the uncertain inputs. Basically, the main idea here is that this type of low fidelity model is very efficient because it's constructed adaptively, and the adaptivity is performed with respect to stochastic information, which is what we want in uncertainty propagation settings. And what we observe is that we are given 14 inputs by the physicists with certain bounds that represent their uncertainty. And what we notice is that once we find this low fidelity model, we compute the sensitivity indices of all parameters, we observe that only a handful of these parameters are actually important, which, by the way, is in par with what the physicists expected. So this kind of plot is exactly what they expect in this type of application. But still, we see that we have 14 parameters given, but only a handful are important. And then the question is, can we use this information to further speed up computations? And then, of course, the answer is yes. And how we do it is that after we compute the 14-dimensional low-fidelity model, we also calculate low-fidelity models using the same sparse-width algorithm, but decreasing the input size. So in our experiments, we consider the high-fidelity model, which is given by the gene numerical simulation code. We started with the first low-fidelity model, which has all 14 parameters, and then we slowly decreased the number of certain parameters based on the sensitivity that I just showed you. So we consider a low-fidelity model with only the most 9 important parameters, and then a third one which has only 6 of the important parameters. And the remaining parameters were essentially kept fixed to their mean value. And what we observed in our numerical experiments is that if we compute the mean squared error of these estimators, then we get a tremendous speed up with respect to the standard Monte Carlo estimator. So if you look in the left panel in this figure, there we show the analytical mean squared error, which is computed directly from the formulas without performing any numerical experiments to get an idea about what we expect in this problem. And then in the right panel, I show you the results that were computed numerically. And what we observe is that if we go from the standard Monte Carlo estimator, which uses only the high fidelity model, to the multi-fidelity estimator that uses the high fidelity model and the 14-dimensional sparse-width low fidelity model, we get almost a factor of 2 reduction in the mean squared error. Even further, which is very interesting, is that if we add into the mix also the reduced dimension low fidelity models, we decrease the mean squared error even further, and we get essentially a speed up almost for free by considering these reduced dimension low fidelity models. And if we were to translate this reduction in mean squared error from the standard Monte Carlo sampling to our multi-fidelity Monte Carlo sampling algorithm, if we were to do each simulation on 240 cores, which is what we need for the high fidelity simulation, the runtime will be, and if we were to obtain the most accurate result, which in this case is for budget 1 million, if we were to use the standard Monte Carlo estimator, this would take about 8 days. But if we were to use our multi-fidelity Monte Carlo estimator, this would take about 1 hour. So we see that we can get tremendous speedups, and these speedups will become even more important when we go to even more complex applications, such as nonlinear applications, in which, as I said, one simulation can take hours or even days. And also another interesting aspect here is that the multi-fidelity algorithm separates, the estimation between using the high and the low fidelity models. And usually the high fidelity model is simulated on a supercomputer or on a cluster, whereas the low fidelity models can be simulated on a smaller machine or even a laptop computer. So that's even an added advantage of this approach. And you can find more details about this in the paper that is pointed out at the end of the slide, which we have it on archive. Okay, so before moving to the second part of the talk, I want to pause and ask whether there are some questions regarding the first part.
I guess you can move on.
All right. So in the first part of the presentation, I showed you the multi-fidelity algorithm that was enhanced with reduced dimension low fidelity models. And in the second part of the presentation, I want to talk about our context-aware formulation of the multi-fidelity Monte Carlo algorithm. So basically, what is our goal here? What are our research questions? With this algorithm, we aim to answer the following research questions. So the first one, which is very important and very relevant, especially in the context of data-driven low-fidelity models, is how do we construct low-fidelity models to be used in multi-fidelity settings? Because the underlying assumption is that we have the low-fidelity models available and the multi-fidelity algorithm just uses them in an efficient way. And even more, how accurate do, for example, data-driven low-fidelity models need to be in multi-fidelity methods? Because we know that in standard single-fidelity settings, if we employ a reduced model, then that reduced model needs to be accurate. And we want to see whether this conclusion is also valid in multi-fidelity methods. Surprisingly, I mean, you see in a few slides, the answer is that actually we don't need very accurate low-fidelity models in multi-fidelity settings. And if we were to paint a picture of this, we do the same outer loop problem in which we have a hierarchy of high and low fidelity models to do uncertainty propagation. But the difference to what we did in the first approach is that the low fidelity models are no longer statically given, but rather we construct them in a context-aware fashion. So again, to revisit the setup in the first approach, we are given a high fidelity model that we assume is computationally expensive. And this model is parameterized by the random inputs. We are given a computational budget, and then the task is to estimate the mean of the high fidelity model. Now, if we revisit the multi-fidelity estimator, which again is the linear combination of estimators stemming from the high and low fidelity models, and we look again at the mean squared error of this estimator, we see again that this expression depends on the correlation coefficients and the evaluation costs of low fidelity models. And this will be key into the formulation of the context-aware algorithm. And even more, we observe that this mean squared error term, because the estimator is unbiased, contains only the variance, so we don't have any bias with respect to the high fidelity model, which is great because this gives us an increased flexibility for low fidelity model construction. So we know that even though low fidelity models have an error, this error doesn't enter into the mean squared error formula, which is great. Okay, so to summarize the difference between the first and the second approach before going to the mathematical details, we were to visualize this. So in the static multi-fidelity algorithm, which is what I presented in the first part of the talk, we have a model hierarchy in which the low fidelity models are assumed to be available, so we cannot further improve them. We have the model hierarchy, and then the task is to do uncertainty propagation. In the second version of the algorithm, which is the context-aware version that I will present next, we have the same task of doing uncertainty propagation. We have a hierarchy of models, but the difference is that the low fidelity models are context-aware. And basically, as a general idea, what we do is that the given computational budget is split between constructing the low fidelity models, similar to an offline phase in standard model reduction, and then the remaining budget is used for sampling in the online phase, as similar to the standard model reduction. Whereas in the static version, the entire budget is used only for sampling because the models are assumed to be available. Okay, so how do we construct the context-aware low fidelity models? Basically, the question is, what do we need to know about them in order to construct them? So we need to know essentially their accuracy and cost rates. And by that, I mean that we need to know their accuracy rate as measured by the decay of 1 minus the correlation coefficient squared, which is essentially very similar to what we know from approximation theory. This is very similar to the error that we have when using these reduced models. As examples of accuracy rates, we can have, for example, algebraic, or if we are lucky and we have a nicely behaved problem, we can have exponential or geometric. And besides the accuracy rate, we also assume that we have available the cost rate. And by that, I mean the evaluation cost rate of the models. So keep in mind that in multi-fidelity methods, low fidelity models are characterized by two ingredients. So one is their accuracy, but also their evaluation cost is very important. So we assume we have this available, and examples include algebraic, but of course, depending on the algorithm that we use to implement the evaluation of the low fidelity model, we can have different types of rates. And then having the accuracy and cost rates available, we will construct the context-aware low fidelity models. And for simplicity, I will show you how this happens in the case when we have one low-fidelity model, and then I will show you how this idea can be transferred to the setting in which we have multiple low-fidelity models. So let's assume we have a low-fidelity model that has a given accuracy and cost rate. So what we do in the Contextaware algorithm is that we split the computational budget between constructing the low-fidelity model using N1 high-fidelity model evaluations, and then after we have it constructed, we use the remaining budget for sampling. So that's P minus N1. How to find N1 will be discussed next. So basically, if we were to write down the mean squared error of the estimator that depends on this low fidelity model only, we have the same expression as before, but instead of dividing by P, we divide by P minus N1. And then the question will be how we construct this N1. So you can think of this N1, for example, the training size for your neural network. And the trick here, and really the heart of this algorithm, is to relate the mean squared error of the multi-fidelity estimator with the rates, with the accuracy and cost rates that we have available. And if we apply standard algebraic inequalities, we essentially obtain straightforwardly an upper bound of the mean squared error that depends on the rates. And we see that this upper bound depends on both the accuracy and cost rate. So you're not only interested in accurate low fidelity models, but we also take their evaluation cost into account. And basically, having this upper bound available, then the task is, we'll treat this as an objective function, and we'll perform minimization to find N1, which would be the number of high fidelity model evaluations used to construct the low fidelity model. So basically, the task is to minimize this objective. And we were in this setting with one low fidelity model, we were able to show the following results. So first, we were able to show that under very mild assumptions, this objective is convex, which means that we have a minimum exists and is unique, which tells us basically that there is a quasi-optimal, and here I mean quasi-optimal because this objective is an upper bound of the mean squared error and not the mean squared error itself. Quasi-optimal trade-off between exploring, meaning constructing the low fidelity model, and exploiting it in the multi-fidelity sampling strategy. And even more, which is the most interesting and somewhat counterintuitive result, we're able to show that this minimizer is actually independent of the budget. So this grows independently of the budget, and beyond a certain budget, this doesn't grow any further, which tells us essentially that in contrast to standard model reduction, in which low fidelity models need to be very accurate, in multi-fidelity settings, low fidelity models can be too accurate. So there is a point beyond which there is we don't get anything more by further refining the low fidelity model. And I will show you a concrete numerical example of what we mean by this. But this is a very interesting and very surprising result because, as I said, in standard model reduction, we are used to thinking that the more accurate the low fidelity model is, the better. But in multi-fidelity settings, actually, this is not the case, which is great because that means that we can have also models that are not necessarily very accurate in single fidelity settings, but they can be very useful in multi-fidelity settings. So if we were to transfer these ideas to settings with two or more low fidelity models, basically we can approach this in two ways. So one is the so-called global approach, in which we are given k low fidelity models, each with an accuracy and cost rate. We use these traits to find an upper bound of the mean squared error, and then we solve a global k-dimensional optimization problem to find the number of high fidelity model evaluations to construct them. Or we could also do a sequential approach in which basically we introduce one low fidelity model at a time in the mix. So introduce the first low fidelity model, find the number of high fidelity evaluations to construct it, then we introduce the second and so forth, which basically means that we can solve k one-dimensional optimization problems. And this sequential approach also has the additional advantage that it allows us to reuse the theory from the case with one low fidelity model. That being said, I will show you the performance and the advantages of the Contextaware algorithm in two numerical examples. And first, I will begin with a sort of model problem, which is a heat conduction in a two-dimensional spatial domain, which basically, this is an elliptic partial differential equation, which is a setup inspired by a paper of Patera and Roza, in which we have a two-dimensional square, which is tiled into a 3x3 block. And the diffusivity coefficient is uncertain and is parametrized as piecewise constant diffusivity field. And this depends on essentially an uncertain parameter in each tile. So we have 9 uncertain parameters. We have a problem with which is 9-dimensional. And the typical output of interest in such a problem is the average heat flux over the bottom Neumann boundary. So one of the reasons for which we chose this test case is that it allows us to easily construct heterogeneous low-fidelity models, which can give us an impression about the behavior of the context-aware algorithm. So we started with a reduced basis low-fidelity model. And why? Because we know that for such a problem, a reduced basis low-fidelity model is exponentially accurate. So basically, we used an off-the-shelf implementation of reduced basis for such a problem, in which we do an offline-online decomposition, and we use the greedy basis generation. And we know that the accuracy and cost rates, so the accuracy rate, we know that it's exponential, and the algebraic one, the cost rate is algebraic. And to estimate the constants in the rate functions, we did some a few numerical runs. And what we know in the context of this problem is that this reduced basis surrogate is very accurate, but we know that as the number of reduced bases increases, then the cost of solving the reduced system increases as well. So basically, we can think of this in the context of this model problem as an accurate but relatively expensive low-fidelity model. We also considered a regression-based low-fidelity model. And for this, we used the epsilon support vector regression technique, in which we trained on n random realizations of the input. And then we estimated the accuracy and cost rates, which for this problem we know are algebraic. And this low-fidelity model actually needs a large number of samples to be accurate, because remember, we are dealing with a 9-dimensional parameter space, but it is cheap to evaluate. So we can think of this low-fidelity model as a less accurate low-fidelity model, but rather cheap to evaluate. And if we start by looking at the context-aware algorithm with a reduced basis low-fidelity model only, we first look at the number, the context-aware number of high-fidelity evaluations to construct this model, meaning the number of reduced bases for increasing budgets. And as the second proposition that I showed you states, this number is independent of the budget. And we see here that as the budget increases, this number doesn't increase beyond 20. So we see that in our context-aware algorithm, basically, we don't need more than 20 reduced bases to construct the reduced basis low-fidelity model. And to sort of emphasize the conclusion that in multi-fidelity settings, low-fidelity models can be too accurate, let's look at the following plot. So in this plot, I depict the mean squared error of Monte Carlo estimators for budgets from 1 to 1,000 seconds, in which we compare the standard Monte Carlo sampling estimator with the multi-fidelity estimators. And what I did is that I used the same reduced basis low-fidelity model, but in which first I constructed it using an a priori chosen number of reduced bases. So as we do in the static version of the multi-fidelity algorithm. So I chose 2, 8, and 50 reduced bases. And I also employed the context-aware multi-fidelity algorithm, in which, starting from the rates, I constructed the reduced basis low-fidelity model, which we know that requires at most 20 reduced bases. So interestingly, what we see, first of all, is that the multi-fidelity algorithms are more accurate than the standard Monte Carlo sampling algorithm. But interestingly, if I use 2, 8, or 50 reduced bases, this doesn't matter, because the context-aware algorithm is actually more efficient here. So with using at most 20 reduced spaces, actually I get more accurate results than if I use 50 reduced spaces. Which is a consequence of the fact that if I use 50 reduced spaces, which is great, this gives me a very accurate low-fidelity model, but its evaluation cost outweighs the accuracy. So we see that indeed low-fidelity models can be too accurate. And of course, if I would have guessed that I need 20 reduced spaces, then I would have gotten the same results as in the Contextaware algorithm. If we go further and we add also the regression-based low-fidelity model into the mix, and we compute the number of high-fidelity evaluations using either the sequential or the global approach, we see again that the number of high-fidelity evaluations to compute these models is bounded, as the theory predicts. So again, we have the same conclusion that beyond, let's say, budget 10,000, there is no point to refine further the regression-based model. And interestingly, if we plug this into our framework, we see that we get even more variance reduction, which is interesting again because the regression model here, which is constructed with you at most 10,000 samples, is actually quite inaccurate on its own. So it's probably a model that you would not use on its own in a single fidelity setting, because in order to get an accurate approximation, you'll need a large training size. But here we see that with the 10,000 training size of 10,000, we get actually even more variance reduction. And let's go a bit further to the more realistic problem, in which we consider again plasma microturbulence simulation. And here we took a test case that is based on a discharge from the Aztec subret experiment, which is a device in Garching in Germany. And to keep the story simple, we considered 12 uncertain parameters. And we had a high fidelity model that is again based on the gene numerical simulator with 276,000 degrees of freedom. And basically here, to get a better overview about our Contextaware algorithm, we considered first in the mix a static low fidelity model, which is given by a cos-width approximation. So we went from 276,000 to 48,000 degrees of freedom, because we see that in this case, the accuracy is actually retained very well. And we got the cos reduction of about 6. And we also considered two data-driven low fidelity models. So the first one is a sparse-width-based low-fidelity model, as in the previous algorithm. But in this case, we measure its accuracy and cost rates. And we see that for this problem, these behave, so these are algebraic. And we also considered a deep neural network. And this deep neural network is actually very basic. So we considered a fully connected feed-forward deep network with 12 hidden layers. And to ensure that as the size of the training set increases, the evaluation cost of the network also increases, what I did, I employed a heuristic and I took the training size over 20 neurons per hidden layer. And once after I did the simulations, I plotted accuracy and cost rate evaluations. I saw that actually they fit very well on an algebraic line. So we have two low fidelity models with algebraic accuracy and cost rates. And now, if we plug this into our Contextaware algorithm by first looking at the sparse-width low fidelity model, with or without considering the cos-width model as well, we see again that as the theory predicted, the number of high fidelity model evaluations to construct this reduced model is bounded, and it's actually very small. And even more interesting, which I think is one of the most interesting results of this work, is the fact that if I consider the cos-width model, I consider the adaptive sparse-width model and the deep neural network, the algorithm predicts that the last two, so the data-driven models, require only a handful of high-fidelity model evaluations to be constructed. So basically, the sparse-width model requires only 405 high-fidelity evaluations, and the deep neural network model only 263 high-fidelity evaluations. So basically, if you want to use a neural network for uncertainty propagation, if you use our context-aware multi-fidelity algorithm, it is likely, it's not guaranteed, of course, but it is likely that you can get away with only a handful with the training size of a very small size, which is great. And if we were to look at the sample distribution, which is generally valid for multi-fidelity algorithms, we see that going from the standard Monte Carlo algorithm, which uses only the high-fidelity model, so basically all evaluations go to the high-fidelity model, multi-fidelity algorithms generally put very small effort into the high-fidelity model. So we see, for example, in this problem, if you look at the rightmost bar, we see that in the context-aware algorithm in which we use the high-fidelity model and the 3 low-fidelity models, only a very small percentage of the total number of samples is invested in the high-fidelity model, which again is great because in these types of problems, I do the simulations for the high-fidelity model on a supercomputer, but the low-fidelity simulations, I can do them on my laptop, which is very convenient. And this is still work in progress, it's not finished, but if you look at the mean squared error, we see that for the same budget, which in this case is 5 million seconds, if we go from the standard Monte Carlo estimator to the further to the multi-fidelity, static multi-fidelity estimator with the closed-width model and then going to the context-aware algorithm, we see that we get up to a factor of 2 improvement, which of course is great. So to summarize, in this presentation, we first looked at low-fidelity models in uncertainty quantification in single-fidelity settings. And we see that in such a setting, the accuracy of the low-fidelity model determines the accuracy of the outer result. Then we discussed about low-fidelity models in static multi-fidelity settings, which are generally leveraged for speed up, whereas the high-fidelity model is kept into the loop to guarantee accuracy. And we looked at an application in which we considered reduced dimension low-fidelity models. However, in these standard settings, it is assumed that the low-fidelity models are available and given to us, so we cannot improve them further. And then we answered the question of how to construct low-fidelity models in multi-fidelity settings in the context-aware algorithm, in which we split the budget between constructing the models, similar to an offline phase, and then using the remaining budget for sampling, similar to an online phase. And then we showed, surprisingly, that in these settings, low-fidelity models can in fact be too accurate. And with that, these are our references. So for the context-aware part, we have a paper under preparation now, which we'll submit soon. For the first part of the talk, we have a preprint available. And then also I laid out some of the foundational ideas in my dissertation. And with this, I want to thank you for your attention, and I'm happy to take questions.
Thank you so much for the great talk. It was very wonderful and interesting.
Thank you.
Let's have a Q&A session. I do not see any question from the chat room, but if you have questions, please post your question in the chat room, or you can unmute yourself and then ask questions. Okay, while you are preparing your own questions, I have questions about overall algorithm. For the low fidelity models, depending on which models you choose to use, there must be some training cost, right? And
yes.
And I think the context aware the algorithm, the one you presented at the end, that is, you're separating the budget for the training and also the online evaluation separately.
Exactly. Yeah, so starting from the accuracy and cost rates of the low-fidelity models, you spend part of your budget to construct them, and then you spend the remaining budget in doing the sampling part.
Right. And then when you set those budgets, you do the training in adaptive way.
So the training, it depends on the low-fidelity model itself. So for example, in the case of the sparse-width model, that is done adaptively because that's the nature of the low-fidelity model. But in case of the deep neural network, for example, I just selected random samples in the parameter domain. So the way you do the training depends on the low-fidelity model itself.
Okay. Well, then quality of for example, that neural network based, low. That will depend on the quality of the sampling.
Yes, yes. So the experimental design is not taken into account explicitly, but rather this will be reflected in the constants that you get. And that's a very good point. So if you change the experimental design, it will also influence the way the algorithm behaves. But this is not directly incorporated into the training procedure, but rather it is reflected in the constants that you get on your rates. But it is a very valid point. So you can, if for example, you do the neural network training differently, then you might get actually better rates. But this is up to you. So this is not prescribed by the algorithm. The algorithm just tells you, if you give me these rates, then I give you this number of the training size. You train your model, and then you do the sampling part.
Okay. Well, okay. So I'm just curious. How bad, the low fidelity model could be? I mean, it's in terms of.
So I don't think there is a sort of measure of how inaccurate it can be, but rather this inaccuracy will be reflected in the way the algorithm behaves. So for example, if you have a very, very inaccurate low fidelity model, you'll see that if you plug it into your multi-fidelity algorithm, the algorithm decides that because this model is very inaccurate, it will invest most of the effort into the high fidelity model.
I got it. Okay.
But in our experience, we actually worked with low fidelity models that are, of course, not complete garbage, but rather low fidelity models that you would not use on their own. So they give you something, but not something very accurate. Now, what this means is, of course, is application dependent.
Right.
But it is very unlikely that you'll need very accurate low fidelity models. I mean, that's the beauty, because you keep all models into the loop. The algorithm will compensate for the bad predictions of the low fidelity models by using the high fidelity model from time to time.
Well, I understand that depends on the application, but if you can give some some definite number with a maybe one of the numerical results you have shown, do you have any idea how low fidelity
So
model?
from my experience so far, if I had a low fidelity model with a correlation coefficient of, let's say, 0.80 something, 0.9, that was good enough for the multi-fidelity algorithm. But also a different aspect that you need to take into account is the fact that if you have an inaccurate low fidelity model, if that low fidelity model is cheap to evaluate, that actually is a plus. So this brings something to your algorithm. But very concrete numbers I cannot really give you, but I can only tell you that you can use, let's say, inaccurate low fidelity models. So if you have a nonlinear high fidelity model and use a linear low fidelity model, that should be perfectly fine.
All right. Let me pose my question here. And how about is there any questions from audiences? I don't see any question in the chat room. You can unmute yourself and ask questions. It's rather a comment by Simon. This was grossing talk. Thank you. By Simon. Okay, thank you.
Thank you. And of course, if you are interested in these things in more detail, you can always shoot me an email and we can discuss further.
Yeah. I mean, we do a lot of uncertainty quantification in the lab, so they must be really interested in your work. Let me ask another question then. I don't know how you did for the reduced basis, the low fidelity model. Did you do that in adaptively or?
Yeah. So I used the reduced basis MATLAB implementation.
Yeah.
And I used essentially an out of the shelf. So they use a greedy algorithm there.
3D algorithm. Okay, so you could apply that in adaptive fashion.
Yeah, actually, also in most of my work, I use this adaptive sparse width interpolation, which I mean that's an adaptive algorithm as well. And basically, the context-aware algorithm then answers the question of what tolerance should I use for the multi-fidelity setting. And that usually is not as low as you would think, which I mean, that's really the main point. But yes, I mean, adaptive algorithms are, of course, much better suited for this type of problem because it means that generally we need a smaller training size than for a non-adaptive algorithm.
All right. One last question from me.
Yeah.
Is there some sort of software available? I mean, to implement?
Not really, but you can ask me about that. I mean, like, I have software available, so I can give this to you. And also, I think Ben Bersdorfer has a small GitHub. So if you go on his webpage at the Grant Institute, he has a MATLAB code that implements the static algorithm. But to my knowledge, there is no package out there. But I can, if you're interested, I can give you my code.
Okay, sounds good. All right. Okay. The Jeremy stated the George Box statement. All models are wrong, but some are useful. Updated. All models are wrong. So you
Yes.
good.
Or most of them, yes. And even models that are not necessarily useful actually can be useful, which is very good.
All right, sounds good. All right, I guess I don't know if there is no further questions, we can end here. Oh, okay. Hongyu asked, how about scalability to 3D? Okay, that's good.
3D meaning 3D in space. Yeah. Yeah, so actually we are currently in the process of starting applying this into a 5D gyrokinetic problem. So it shouldn't be a problem to be scaled there. It's just a matter of how many resources are you willing to invest. And of course, the more expensive the high fidelity model is, then the more expensive everything will be. But the scalability problem really translates into the low fidelity models that you have. So this should be applicable to any type of problem. So it's no limitation there. It's just a limitation on how many resources you need. Because if you have an application that takes 1 week per run, then that can become problematic. But this type of application can make your life easier. Because if you need to invest only 10 high fidelity runs and 1 million low fidelity runs, then you can do it because you can do 10 supercomputer simulations and then 1 million simulations on your laptop, which costs nothing.
Yeah. I mean, some of the applications we are running, it may take a week.
Yeah. Yes, I recently finished a nonlinear plasma study in which, for the moment, is only single fidelity, and that took 56 simulations, but those simulations were very costly. So, but it will be relatively straightforward to transfer that settings, so we can go, even more accurate. So yeah, you can do it. It's just a matter of how many resources you are willing to invest.
Yeah, sure. All right. Thank you. I don't see any question from chat, so maybe with that we can end the seminar today.
Thank you so much.
Thank you so much for the great talk.
Thank you for having me.
Yeah, and we may, I may invite you again for the second talk.
Yep. Just let me know. I will be happy to give another talk on a different topic this time.
Yeah, but until then, please take care.
Okay. Thank you so much for having me again.
Great.
We'll keep in touch. Okay.